Okay, I think we're gonna get started here. Okay. Alright, so today we're gonna be talking about feature design. And before we get to the lecture content, as usual, there are a few housekeeping items. So first up on that list is that there are tutorials this week. Like before, they're in the evenings. This time they're on the 6th and the 8th, so Wednesday and Friday. This will be a tutorial on scikit-learn for the most part. This is a machine learning library in Python that you'll be using in the next mini project, which I'll discuss in just a second. So this is a very useful tutorial if you've never used scikit-learn, don't know what scikit-learn is, possibly useful for those of you who've already used it in the past. And one other thing I will mention about this tutorial, so I made a My Courses announcement about this too. So the first half of the tutorial is going to be the standard scikit-learn tutorial that we give in this course, but the second half, there's actually going to be a demo of an intelligent tutor. So this is a AI-based tutor for machine learning. It's developed by a PhD student at MILA, so this is the Montreal Institute for Learning Algorithms. It's a group I'm affiliated with. It's the largest academic machine learning and deep learning lab in the world. So Julian is a PhD student there. He has this intelligent tutor that they're trying to spin out into a little company, and so it's pretty interesting, pretty exciting. So that's the second half of the tutorial for those who are interested. Basically, it'll be both a kind of tutorial on a bit more of general machine learning concepts, but the tutorial will be in principle given by an AI. So it's kind of a funny idea, interesting for those of you who want to stick around for it, and that'll plan start for that is around 7:30, presuming there aren't a ton of questions on the first half. So that's a bit interesting, a bit different. The other quick thing I want to note, made an announcement about this just before class, is that this week I have to move my office hours. So I'll be doing them tomorrow morning from 9 to 11 a.m. in the usual spot. So I'm sorry about that. This will hopefully be the only time I have to do that during this semester. And I will say also that as we get closer to final project and midterms, I will have a second office hours during kind of the really intense weeks there. In case people are worried that they won't be able to make my usual office hours and, preparing for the midterm and so on. Okay, and probably the most important thing is that Mini Project 2 is now available. So I hope everyone got some rest after Mini Project 1. Mini Project 2 is a little different. So again, you're going to be in groups of 3. The general kind of outline is the same. But in this project, the idea is we're going to do some sentiment analysis. So for those of you who haven't heard of the term sentiment analysis, this is a relatively popular application of machine learning and natural language processing. And the idea in general for sentiment analysis is you want to do some predictions, usually based off text. On Twitter, it's pretty common to do this, where your goal is to classify the kind of attitude or sentiment of the text, say, towards some company or some product. So this is a very important application for, say, financial companies. There's actually a very, very famous, somewhat of a mess-up where at a time when Anne Hathaway, I can't remember what movie she was in, but she was in a very poorly reviewed movie, Anne Hathaway, that had a lot of negative sentiment on Twitter, and that actually decreased the stock of Berkshire Hathaway. So Berkshire Hathaway has nothing to do with Anne Hathaway, but because there's all of these sentiment analysis systems and people trading stocks based on them, they saw Hathaway was really negative, but really it just had to do with Anne Hathaway. So they're not perfect. It's an interesting area. It's also, in some sense, a bit of a fraught area in general in terms of, in machine learning, we often like to talk about having gold standard data. So our idea is, we're trying to predict say whether or not tumor recurs. And we know we have a training set of here's examples where a tumor did and where a tumor did not recur. But for sentiment analysis, we're talking about a subjective phenomenon. And so it's a little bit harder to say, what is the ground truth? Is this tweet positive or negative? So in this project, we're going to be looking at probably the most straightforward example of sentiment analysis, and that is we're going to be looking at IMDb reviews and classifying whether or not these reviews are positive or negative. So here we do have a ground truth in the sense that we know what the rating of the review was. So if somebody gave a really low scoring review, we're going to presume that's low sentiment. Really high scoring review is high sentiment. This is just going to be a binary classification task from your perspective. You don't need to worry about neutral reviews. We're only looking at really negative and really positive ones. And how this mini project is going to work is you're going to build some different models. There's some specific requirements. For example, we ask you to implement a simple naive Bayes model from scratch, but otherwise you're pretty much free to do whatever you want. But you're going to compete against one another to try to get the best accuracy on this task. So we're going to use this platform called Kaggle. This is a platform that became popular a few years ago. They host machine learning competitions. If any of you are really interested in these sorts of competitions, some of them actually have large monetary prizes. I will warn you, they are very hard to win, especially in these days. There's some people who kind of make it their almost more than a hobby into almost more of a job doing these Kaggle competitions, but ours is a private, closed competition just for this course. So in the assignment specification, you'll have a link that'll let you sign up for this competition. You have to sign up as your group, so as before, you're going to be in groups of 3. Your team, register on my courses, use the same team name, so your number from my courses when you make your team on this Kaggle competition. And the way this works is you'll go to this website, this link. There'll be some information. It'll let you download the training data. It'll tell you kind of about the training data. And then you're going to submit your predictions on the test set. And then on this leaderboard, it's going to say how well you did. But an important thing to know is that this leaderboard is only based on 30% of the entire test set. So this is to prevent people from overfitting to this leaderboard. So generally, this leaderboard is going to be a good indication of how well your model is performing, but you can't hack the system by just kind of tweaking things until you do better and better on this leaderboard. Really, the right thing to do is to use the training data we give you to develop some validation set or some cross-validation technique to use, and then use that for all of your model design and only submit to the leaderboard when you think you have a good model. You're also only allowed to submit 2 submissions per day. So again, we're really preventing you from trying to hack this leaderboard. And this does have an impact on your grade. So grading is 20% for just getting things done, basically, and having your results actually be reproducible. This is another really important thing. Your code, in principle, has to be able to reproduce your submission to the leaderboard as well as anything in your report. So 20% is just kind of getting things done. 30% of your grade is going to be the write-up, so we're again going to ask you to do a write-up. It's a bit more kind of free than the previous one in terms of what you can include there. And then 50% of your grade for the mini project is your performance in this competition. And how the grading works is it's a linear interpolation from random to whatever the best performing team is in the course. So what this means is that if you're all kind of bunched up, everybody's getting around, say, 89, then it doesn't really matter if you're not, in the top 10, because it's going to be a linear interpolation. So the formula is in the assignment spec if you want to kind of run some numbers. But another important thing that I'm instituting this year for this competition is that anybody who beats my baseline guarantees 100% on that portion. So, yeah. I mean, maybe it's not that hard to beat. Hard to say. It's a pretty good model. So that's kind of but then the top 3 also get some bonus points. So even if you beat mine, you still might want to fight for those bonus points. But I'm instituting this because basically, if people do get up into the low 90s, which is about as high as I've ever seen people get on this data set, I don't want people to be stressing about fighting over the last bits of points. So basically, the idea with this is that if everyone's doing really amazing, everybody can guarantee getting full grades on the competition part, unless you want to pour a bunch of hours fighting for those bonus points to be one of the top teams in the course. So that's how the scoring is going to work. I've also put up
So there's a random baseline. You should do better than this. There's a basic naive Bayes. So this is just a reference point for when you implement your naive Bayes model for where you should be. So it's about 83. It's a little bit hard to read. There's going to be slight differences depending on how you process the text. It's not going to be like assignment 1 where we were expecting everyone to do all the pre-processing and everything in the same way. But even so, your naive Bayes should be in the low 80s. That's kind of a good sanity check that you've implemented it correctly. And so, like I said, you get 2 submissions a day. This is open until the deadline. Late submissions, it'll be open, but we'll mark those as late. So that's the basic outline for the mini project. So it's a little bit different, a little bit more kind of free to do what you want. And the scikit-learn tutorial will be very helpful because I highly recommend using those models for this project. Is there any questions about the project at this point? Yeah. No, great question. So do you get any deductions based on the number of submissions? No, there's just that limit that you can only make 2 a day. And you'll also remember that you have to select which submission you want to be your like top 1 at the end. Like we won't automatically take your best scoring one if you keep submitting things and then you're like, oh, I want to go back to my old model. Make sure you kind of select that one as your model. Yeah. Ooh. That's a good question. I'm not sure, actually. That's whatever Kagel's default is for that. I'm going to guess that it's per calendar day. Okay, cool. So now moving on to the lecture. So today we're talking about feature design. So in this course, we're of course talking about machine learning, and the main steps in solving a supervised learning problem, which is what we've been discussing so far, and what we'll continue discussing for most of this course, is step 1, we have to decide what is our input, what is our output. We have to decide how to encode our inputs and our outputs. We have to choose a model, so hypothesis class. Are we using a linear model? Are we using naive Bayes, etc.? We have to choose our error function. And then we have to choose our algorithm, our kind of procedure for how we're searching through the different model spaces. So we're doing cross-validation. How are we doing this? And really, so far in this course, we've been pretty focused on the models, on the idea of cross-validation, on the idea of the error function and the loss function. And we've been pretty much assuming that we just have our inputs and our outputs. We talked a little bit about feature transformations, but really we've been presuming that, say with our recurring tumor example, that we know all of these features. Or for the spam email, that we have these set of features given to us. So today we're going to discuss something that most machine learning researchers spend, frankly, the majority of their time on, which is feature design. So figuring out what are the encodings of our inputs, what are we using as our inputs. And we're going to have a focus in the text or language space. This is because Mini Project 2 is about text classification. This is also building off of Mini Project 1. A lot of people were kind of confused at how simple and naive our text features were in Mini Project 1, where we asked that you just kind of split all the text by white space and then do word counts. Yes, that is not the best thing to do, and that's what we're going to talk about today, and you're going to have to do better than that if you want to beat my baseline on the Mini Project. So what are the key steps in feature design or feature extraction? So usually we assume we're starting with some raw feature data. So using the text classification example, looking at IMDb reviews, we have our review text. It's our raw data. The next thing we're going to do is we're going to construct a number of features from this data. So we might take word counts, we might do all kinds of things that we'll discuss in a few slides. So this is the feature construction step. The next step, which we haven't talked about really very much at all, is the feature selection step. So I come up with a whole bunch of crazy features, and some of those are going to be better than others. So how do I decide which features to use? We could just do cross-validation with all different types of subsets, but maybe we want to be a bit smarter than that, because it can be expensive to run our model over and over and over again. So what are some strategies that we've talked about in course? Some of these We've discussed formally other of them. I've just kind of mentioned offhand here and there. So, of course, you can use domain knowledge to construct features. You can do word counts, for example, with the spam email. I've mentioned a few features, like maybe you want to look at the time of day. In general, for most problems, you're going to have to incorporate some domain knowledge in order to come up with good features. The other things that were briefly discussed, a little bit more actually on the discussion board than actually in lecture, is normalizing our features. So you might not just care about the size of a tumor when you're predicting the recurrence, but you might care about how big that tumor is relative to the other examples. So there's normalization across different features. So you might want to say that, oh, I want to make sure that my feature that is related to how many times the word, the occurs isn't so huge compared to my feature for the word dog, because they have very different frequencies, so we might normalize in that way. We normalize across instances. These procedures can be very useful for making our models run better. They can actually improve performance, so it's not just a minor thing to normalize, it can help a lot. We discussed these nonlinear expansions. So this is probably the main feature kind of construction technique that we explicitly discussed in class. And that is things like taking the product of different features, taking the square, taking the cube, taking the log. And these things can help quite a lot. If anybody tried these in Mini Project 1, they actually did help. If you used one of the features, you could get a pretty big gain just by doing some nonlinear expansions of those features. So these all work well, and actually, as we'll discuss, you can view regularization as kind of a way of incorporating kind of a feature selection strategy into your model. So these are things we've discussed. So kind of high-level ideas that are going to work well all the time. But today we're going to talk about some more advanced methods, starting with a bunch of techniques for extracting useful features from text. And then we'll follow on that with strategies for actually reducing the size of your feature set, supposing that you've selected or you've constructed a huge number of potentially useful features. So why do we actually do feature design? So why is this, like I said, one of the most important parts of machine learning? Why is this the place where people spend a lot of their time? Well, first off, feature design is probably the biggest way that you can improve your predictor performance. So oftentimes when you're starting off in machine learning, you get the perspective that the big thing that's going to give you gains is using a more complicated model, going from linear regression to some sort of nonlinear neural network or a decision tree or support vector machine like we'll talk about next week. And this is true to some extent that using better models can help, but almost always if you can find a new clever feature, the delta you get, the improvement you get from that new feature usually dwarfs anything you get from comparing different models. This is not true like always. Some models are generally not very good, but it is the case that coming up with new features, especially if you're talking about applied machine learning in, say, an industry context, where you have access to all kinds of unstructured data you can extract different crazy features from, this is going to give you, for the most part, the best bang for your buck. The other thing that you might want to do feature construction for and selection for is to improve the runtime or the performance of your model. So things may be working okay with a whole bunch of features that kind of came up, in a very kind of ad hoc way, and they seem to work, but maybe your model's really inefficient. Maybe you could do better with just 3 really good features. And then lastly, is kind of an interesting one, but improving interpretability. So coming up with crazy features, crazy nonlinear transforms might improve your validation accuracy, and oftentimes that's good, that's what we care about. But sometimes it can be really satisfying to come up with a really nice interpretable feature that is, some say, maybe it's a summary score that summarizes a lot of other insights you have, say in spam emails. You come up with some really nice feature that gives you a lot of gain, and that can be super useful because if that feature is really informative, then you can say, oh, well, I know why my model made this classification. It's because it has this value on that feature. And when you have a model that has squared term and a log term and a cubic term, you're like, oh, well, I classify this as spam because the square of the time of day that it was written at was really high. You're like, okay. So improving interpretability is actually a useful thing that we can do by designing good features. And again, the important things here is we want to design good features, but we don't want to lose information, and we don't want to overwhelm the model and ourselves by having too much crazy stuff. So there's coming up with features, and then there's kind of whittling down these features. They're kind of part of the same process. So what are the types of applications where we see lots of features, where feature design becomes a very big deal? So there are some data sets, again, coming back to the tumor example, where a doctor says, look, here's the set of variables, set of features I have about a tumor. How well can you predict recurrence? There isn't too much you can do in terms of feature design in a setting like that, because you're basically given the universe of features, a pretty restricted universe up front, and it's going to be really intensive to ask the doctor to come up with some other new feature or do some new tests, etc. But three domains where there is a ton of features that you could use and where feature design becomes really important. So first off is images and video. So there's all kinds of ways to derive features from image data or video data from pixels. We're not going to talk about this today because this is a place where modern deep learning methods really kind of reign supreme. But it is an application where feature design is extremely important. Another one is biomedicine, and in particular working with gene expression data. Again, this is a place where it's super high dimensional, tons of information, and it's very hard to even kind of yourself come up with features. You need to use these automated techniques to extract subsets or come up with new features. And then natural language processing, which is what we're going to focus on today. And this is a really nice case because, for one, there's lots of different words. It's a really rich, structured input. But there's no natural way, if I just give you a sentence and I say, make a feature vector out of that. There is no kind of canonical way to do that. So feature design is kind of there from the very beginning when we're doing natural language processing. When we say, how do we predict the y's from our x's? In natural language processing, when the x is a sentence, what does that mean? What are the numbers that our model is taking in? So in the context of modeling natural language, we're going to discuss a few different types of features that we might want to use. Again, these are all things that could be very useful in Mini Project 2. So we'll talk about how we can encode words, how we can encode words with particular weights, so it's called the TF-IDF method, which is extremely useful. We'll talk about the idea of what are called n-grams, so not just looking at individual words, but looking at, say, 2 or 3 words co-occurring together. Talk a little bit about syntactic features. We will not talk about word embeddings today. So word embeddings are a very useful technique for analyzing text. They could be useful in Mini Project 2, but you will be able to beat my baseline without them. I know that's possible. So they're a useful technique. We'll discuss them once we get to neural networks. And I will just point out now, because it's a very useful thing, it's been mentioned on the discussion board, but NLTK, it's a Python package. It's the Natural Language Toolkit. Almost everything we'll discuss today, NLTK has a function for doing that. Also, scikit-learn has a function for doing a number of these things. So you don't need to implement all of this stuff from scratch. And that's going to be one of the themes as we progress in this course. Mini Project 1, you implemented everything from scratch. Mini Project 2, you do a little bit of from scratch implementation, but for the most part, you're relying on off-the-shelf libraries. And then once we get to deep learning in the final project, it's going to be just impossible for you to implement things totally from scratch. So that's kind of this general shift. And so the expectation, I don't expect you to implement everything in all of these slides by hand. That would take way too long. Use something like NLTK. Okay, so the first important text feature is encoding word information. So how do we encode the presence or occurrence of words? Well, the one kind of natural way we can do this is just with a binary feature. We can just have a binary feature that says, did the word the or did the word dog occur within this piece of text? So I'm showing kind of Simple example here, we have two documents. Apologies if they're difficult to read. So this one says, the quick brown fox jumped over the lazy dog's back. So in this particular document, we would have that the word the occurred. So we put a binary indicator of 1. This actually works surprisingly well. So you think, well, just binary occurrence doesn't take into account how many times that word occurred, etc. But in fact, especially for analyzing short text, binary features are extremely useful. A lot of the state-of-the-art for, say, Twitter analysis just uses these binary features. But of course, you might want to incorporate the actual frequency, so the actual count of the word in this document. So the feature vector for a document is going to be, say you have 10,000 possible words in your vocabulary. The feature vector is going to be a 10,000 dimensional vector where you're going to have an entry for each word, and then the value of each of those entries is how many times did that word occur. And of course, you might not want to have just raw word counts. You might want to have the kind of relative frequency, so how many times did this word occur relative to how many words are in the document, etc. So there's lots of things you might want to do in terms of just incorporating word counts. And again, in a mini project 1, we had you do the simplest thing, which was just this raw count idea. And another minor point that I'll bring up now is that we've been discussing naive Bayes in previous lectures, and we were talking about what we call the binary, or the Bernoulli is the proper term, naive Bayes. When I said this is very useful for text analysis, but you may have noticed that we're always assuming in that entire lecture that we had binary features. So that works well when we have a binary encoding of the words, but you can't run a Bernoulli or a binary naive Bayes when your features aren't binary. So this is just a quick kind of pointer to the fact that in addition to the binary or Bernoulli naive Bayes, we also have the multinomial naive Bayes. So instead of us modeling the output, so the distribution of the features given the class, as a binary coin flip, we model it as a multinomial distribution, so the outcome of n different coin flips. This is what the actual probability looks like. So probability of a particular feature vector given that we have a particular class is given by this multinomial here. In fact, this term doesn't really matter because it doesn't depend on the class. So this is really what the multinomial naive Bayes looks like for this probability, which can give us the likelihood. And I'm not going to go in detail for the derivation here. Just like the binary naive Bayes, there's a little bit of kind of math, but at the end of the day, it's a pretty simple model. And if you're interested in useful homework, for example, it could be useful for exam prep, deriving the maximum likelihood estimate for multinomial naive Bayes is a very useful thing to do. So that's just a quick pointer that we're talking about features, and for the most part, features are independent from the model. You can plug and play different models and different features, but that's not always the case, because with a naive Bayes, the model makes assumptions about the type of features we have. So if these were continuous features, we'd have to use Gaussian naive Bayes. So just a quick pointer that it's not always, feature design isn't always independent from the model. Okay, so we can count words, that's nice. We can count the occurrence of words, how many times, what their frequency is. What are some more things that you might want to do? So again, things that were mentioned on the discussion board for mini project 1. So one is stop words. So common words like the, of, and, about, they're really unlikely to carry a lot of information about your classification task. So for example, we're classifying sentiment. It's hard to say whether or not the use of the is going to indicate that someone has a positive or negative attitude towards something. If we're doing topic classification, these sorts of stop words really don't carry any semantic content that could be useful for the classification. So it's extremely common practice to just remove these stop words. There are standard lists of these stop words. NLTK has a built-in list of English stop words and stop words for other languages, and it's pretty standard to remove these things, though I will give 2 points here. One is that I find that it almost makes no difference to do so. Personally, I haven't removed stop words in many years because, for one, I've never seen it really drastically improve performance, but two, I've seen it actually decrease performance sometimes. So it's an interesting thing. I mention it here because it's a very standard pre-processing is to remove stop words, but I don't explicitly endorse it as a thing you should always do. If you're going to do it, try your model with and without this step. And why does it hurt sometimes? Well, interestingly, doing things like authorship attribution, so I have a bunch of documents, I'm trying to classify who the author was, or I'm trying to classify some demographic attribute of the author. Maybe I'm trying to classify their gender or what country they're from. In fact, stop words are extremely useful indicators. So stop words tell a lot of information about the style of the person's writing. They don't tell anything about the content, so they may be not useful for classifying sentiment or for classifying the topic of an article. But if you're trying to classify, is this article written by person A or person B, stop words are very useful. And in fact, people who do what's called forensic linguistics, so they're actually trying to, so for example, if someone's trying to make an argument in case that, oh, this letter was written by this person and that's relevant because this letter says that they actually wanted to have their will go to person A and not person B, forensic linguistics is almost entirely based off kind of stop word frequency analysis. So it's an interesting thing that, in general, we say remove them, but there's a whole bunch of fun stuff you can do with them. Lemmatization is a very similar story. So lemmatization is this idea that, so words have all kinds of inflected morphological forms. So the example we have here is the word perplexed, or perplexing, or perplexes, and perplex is the stem here. There's a bunch of different words we can derive from the word perplex, but they're all kind of semantically coming from the same word. So we call perplex the lemma in this case. Sometimes you'll hear it called the stem, and there's a slight difference between a lemma and a stem, but we won't worry about that in this course. But the important idea is that a package like NLTK can do something called lemmatization, or stemming, where what you do is you say, take away all of these inflections, all these different morphological forms, and just give me the root word of everything. Again, that can be very useful, say if you're trying to do topic classification. It doesn't matter if someone says running or ran or runs. That article is probably about sports, right? So you don't need to worry about all these different forms, but they might be important, say, for doing authorship attribution. Okay, so that's what we do with words. Generally, we count them, we include some of them, sometimes we map words down together. So now getting into very useful features. So word count features are generally quite useful, but as I've been hinting at, not all words are equally informative, and say, for example, we're trying to classify the topic of an article. Now, which word would be more informative, the word the or the word penguin? Now, I think obviously we would say penguin. That would be more informative if we're trying to classify the topic. And this is the intuition behind what's called the TF-IDF weighting scheme. So this was first proposed by Salton in 1988. It was actually first proposed for helping to run like search engines, but now it's a very useful thing for all kinds of classification tasks. And what TF-IDF stands for is term frequency times inverse document frequency. So what this means is that we want a word to be important if it has high term frequency. So term frequency is how many times does it occur in this document. But we also want it to be a relatively rare word overall. So what's the inverse of how many other documents this word occurs in? So in particular, the TF part of this TF times IDF is just how many times did this word occur in the document. And the IDF, the inverse document frequency, is a little bit more involved, but it's basically just, it's the logarithm of how many documents are in the corpus divided by documents with this term, and then we plus 1 so we don't have a divide by 0. So this IDF term is going to downweight words that occur in all different types of documents. Again, you can think if we're doing something like trying to classify the topic or trying to classify the sentiment of something, right? A word that occurs in every single IMDb review can't be that informative for a classification task. So why don't we downweight this word? And the other thing that's nice here is that you don't need to just use your training data to compute this. Say you have your particular training data, you're trying to classify some reviews, but you also have a large corpus of other text, of review text that doesn't have labels, right? You could use that large unlabeled corpus to compute your IDF weights, and then use those IDF weights to construct features for your supervised task. So this is a case where you can use unlabeled extra data to help give you information about what words might be more or less informative. So a very useful strategy. Yep. Should you? Can you? So is the question, should you apply these weights to... Oh, that's a great question, yeah. So how do we... So here are these weights. What I mean by this is that instead of in your feature vector having the count of how many times this word occurred in the document, you have the count of how many times this word occurred in the document divided by its inverse document frequency. So these don't give you the weights of a model. These just give you a scaling of your features. So these weights that we're talking about are just kind of weights that define your features. It's a great question, though. It's not... TF-IDF used to be a model, but now we just use it as a feature construction technique. Does that make sense? Indeed, yeah. So the question here is, well, if you use extra data and that data, so extra data to say compute your IDF weights, but that extra data is from a very different domain. Say you're doing review classification and you take a bunch of New York Times articles and get your IDF weights from there, that can hurt your model, and it's a good chance it will. And this is going to be a general thing. This approach of using unsupervised data to help is sometimes called semi-supervised learning, and generally it's only going to help you if the large unsupervised collection is really closely related to your supervised task. That's a great question. So of course we don't just look at words. Oh, yeah. This is a great question. So the question is, what do we do with really rare words? Do we generally consider all words? So generally, there's no tried and true way for this. I would say that for the most part, when people work with naive Bayes and logistic regression and these sorts of models, they have a tendency to use pretty much all the words. Obviously, if something only occurs in your test set, then you can't use it because you haven't seen it in the training set. But in general, some people believe in having a cutoff of, I'm just going to look at the top 100,000 words or the top 10,000 words. I'm going to exclude words that have a frequency of less than 5. I will say that if you're using deep learning models, you need to make these cutoffs, and not making these cutoffs is going to hurt your approach. When you're using naive Bayes and logistic regression and TF-IDF counts, generally it doesn't hurt as long as you can still afford to run this big model that has all these features. So there's no exact right answer, but it's a good point that you have to decide which words to include. And something to note with language is words have what's called this Zipf-ian distribution, which means that the word that is, so the word the is basically 10 times more common than the word of. And as we go down the rank of how popular words are, there's this what's called this power law decay. So basically, if we go down to the word that is the 100th most frequent word in English, that word occurs 100 times less than, say, the word the. And what this means in practice is that really the top 10,000 words make up the vast majority of all words in every data set. Most of us come across maybe 10,000 or 30,000 words a day. And so generally, you can get by just using the top 10,000 to 30,000, but sometimes, especially when you're using something like naive Bayes or logistic regression, a rare word, say a word only occurs twice, but that word is like really strong negative word, maybe it's useful to include that in your classification and those models can actually do well with that. So it's a bit of a tricky thing dealing with these rare words, and rare words are in general kind of like the bane of people who work with text data, because really you're expending half of your computational resources representing things that only happen in 1 in 10,000 training examples. Yeah, exactly. So it's an interesting, yeah, so there's one thing is we care if a word occurs a lot in a document, we might care about that word, but only if that's kind of surprising, right? If that word, the word the occurs lots in all documents, so it's not that interesting. But if a word occurs a lot in one document, so it's high term frequency, then we might care about it. So kind of occurring a lot can mean different things, and also again, it gets subtle when you're talking about different classification tasks. Like again, authorship attribution is an example where subtle changes in the frequency of these very common words can actually be very informative. So it's a good point that none of these, there's not always that rare words are more informative or that high frequency words are less informative or that we should always use IDF weighting. Generally, most of the strategies I'm talking about and most of the insights are relevant for sentiment and topic classification. The weird cases of authorship attribution are kind of a bit backwards for intuition. I just mentioned them so people don't think that this is kind of always going to be the right thing to do. It's a great question. Yeah, so this is another good question about how about considering the lengths of the texts. So for one, we can do that obviously in our term frequency counts. Instead of just saying how many times does this word occur, you can say how many times does this word occur divided by the length of a document. But for this inverse document frequency thing where we're saying how many documents does this word occur in, if there's big differences in the lengths of documents, that can also cause subtle issues. Again, there's something called Heap's law, which says that as you get longer documents, you're more and more likely to see rare words at a particular frequency. So I wouldn't stress about these kind of things for this project, but in general, controlling, especially if you're trying to integrate different data sets where the documents have very different lengths and things like that, or analyzing documents over time where there's historical shifts in the lengths and styles of documents, these kind of things can be huge pains. But when you're working, say, with IMDb reviews, most of them are around the same length. You don't need to stress too much, but it might be reasonable to not just look at the raw count, but the actual frequency in the document. Cool. Any more questions before we move on? Awesome. So, up till now, talking about words. Words are very useful. They can get you most of the way, but sometimes it's not just words that are interesting, but actual co-occurrences of words. The classic example you could use is that it seems weird to split the phrase New York into two words, new and York. Really, that is a phrase on its own, New York. So one thing that we often do is we don't just look at individual words, which we call unigrams. We also look at bigrams or trigrams. So instead of just saying the quick brown fox jumped, we have 4 words there, we can actually say, oh, we also have 3 bigrams or 2 trigrams. So quick brown as being kind of an individual unit. And we can say how often do we see quick brown together. We can get IDF and TF scores for quick brown. So this can be very helpful, again, presuming that you have the computational resources to deal with the fact that you're going to get an exponential blow up in your number of features here. But can be very useful. Generally, we only ever go up to trigrams. Even just getting counts for 4 grams is extremely time consuming. But these can be very useful. The other things that can be very useful besides just looking at words is actually looking at some of the syntactic structures in the sentence. So you might care about how many, say, how many times a word occurs as the subject versus the object in different sentences. There's all kinds of interesting. You might even count, say, how often does this person use personal pronouns? So personal pronouns is actually an interesting one where you can predict, say, the likelihood of a user staying in an online community by how much they use I versus we, things like that. So sometimes you want to look not just at the words, but at syntactic structures. So yeah, pronouns very useful, verb uses, tenses. Maybe somebody talking in the past tense a lot is indicative of particular things. In fact, for reviews of not movies, yep. It's a good point. So it's like, in principle, the space is exponentially blowing up, but in practice, it's very sub-exponential. So you don't actually, like, it would be a very silly thing to do to say, take all words in my vocabulary and take the cross product of that and then have a for loop that says, for all pairs of words, check if they occur. Much smarter to say, just chunk up my text into pairs of words, because the number of bigrams you actually see is far, far lower than the number of possible bigrams there are. It's still a big blow up, but you're right. It's generally, though it's in principle worst case exponential, generally sub-exponential. But yeah, so syntactic features can be very useful. A fun example from this is actually in restaurant reviews. People who discuss restaurant reviews in a narrative fashion where they say, I came in and I sat down and then this happened, those generally tend, if I'm remembering this correctly, to be very negative reviews. So it's weird. Like, there's actually these sorts of tweaks in how people write things that you can pick up. These are very advanced features that something like NLTK can help you, but it starts to also take a little bit of linguistic knowledge. So some people who do NLP are also linguists, and that can be helpful. So these syntactic structures are useful, also semantic structures. So you might care about not just the fact that some words have the same lemma or root, but some words are also synonyms of each other. So you might want to collapse those together. These are called syn sets, and things like WordNet can help you with that. This is a great question. So the question is, how do we even know automatically what the part of speech is? So is it a verb, is it a noun when this word occurs? Because it can be ambiguous, again, because, for example, the past tense of many verbs are also adjectives. In fact, this is a natural language processing task itself. It's called POS, for part of speech tagging. POS tagging is not a super active area of research now. On the main benchmarks, the consensus is that we're like pretty close to the performance of a human annotator. But if you use NLTK and you say, give me the parse of this sentence into which things are verbs, which things are nouns, which are adjectives, it's important to know that that's not ground truth. That is the prediction of another machine learning model. And this is something that, again, as we progress in this course, kind of things build up. And then we start getting our features are coming from other machine learning models that we've already trained. So for example, we're doing a mini project 2 on sentiment analysis, but people often use sentiment scores as features in other models. So again, it's coming from the output of another model. So it's a great question. Can't always trust POS taggers, but they're generally pretty good. So these are interesting features, these kind of more advanced linguistic features, but they can be a little expensive. And then really quickly, the last thing that can be useful, especially for sentiment analysis, is not just for... Yep. Oh, yeah. Yeah, so the question is, might you want to consider the position of the words? Definitely. So it's not that common to say where in the... is this the first word in the sentence or the second? But people use statistics, so you can not just get the part of speech, but actually get a parse of the sentence where you parse it into a tree that tells you the syntactic structure of the sentence. And you can use statistics from there to say, is this word the root of a high up node in the tree, and things like that. And these can be useful features. but they're generally pretty expensive and don't give you too much gain. Oh, for the whole text. So the question is, what about not just in a sentence, but in a whole text? Yes, that's an interesting one. You could use that. I've never actually seen that that I know of, but it seems like a very reasonable thing to do. For example, for classifying the topic of news articles, it's usually the first couple sentences is all you need. So maybe a useful feature, yeah. So the other useful features I'll quickly mention is what are called sentiment or affective lexicons. So words have connotations associated with them. Hate, generally a negative word. Love, generally a positive word. And there are lists that map words to scores for their connotation. So one, I've linked to them here, one that just has a list of positive and negative words. There's this other data set where they actually have continuous ratings of how positive or negative a word is, so-called the valence of a word. There's all kinds of these lexicons. They can be pretty useful, not even just for kind of emotion words, but also in this data set called Luke. It was developed by some psychologists at UT Austin. It actually has all kinds of crazy categories, like these are words associated with cognitive mechanisms and interesting things like that. And sometimes these things can be very useful for classification tasks. Okay, so that is a whole bunch of different types of features we could extract from text. But what if we've extracted just a crazy number of features? We ran a bunch of lexicons, we have scores, we have bigrams, we have trigrams, so on and so forth. We have thousands, maybe even millions of features. Now, this might not always just work because our model might be overwhelmed by those. It might be overfitting. It might be too expensive to run. So sometimes it's necessary to do feature selection. So now we've built up all these features, and we have this huge matrix. We have our n examples. We have our m different features. But frankly, m could even be bigger than n, and we know that that's going to make, say, something like linear classification or linear regression give us a singular value exception. Because this is not going to be an invertible matrix. So a challenge is, how can we take this big, fat, wide matrix and just select a useful subset of these feature columns? So what are the three kind of classic feature selection techniques? Yep. Yes. Yeah. So generally, three approaches that are pretty popular. First one is using principal component analysis. So if people remember their linear algebra, eigenvalue decompositions are coming back. Variable ranking is another one. So here we're trying to figure out which of the features are most correlated in some way with our output. And then the last thing that people do is what are called representation learning. And this is where we're building a really complicated model, a deep model, that actually learns to implicitly do this feature selection through the learning. And this is what deep learning is, or called representation learning. And we won't talk about this today. This is the topic of kind of the second unit in this course. So, principal component analysis. Here the idea is we have our original huge feature vector for all of our points, and we want to find some way to project this feature vector into a lower dimensional subspace to reduce the dimensionality. And the way we're going to do this is using a linear mapping. So it's, in some sense, the most straightforward way you could think about it. We have some high dimensional x vectors in an m-dimensional space. Let's project those down to a lower dimensional space of dimension m prime by just applying some transformation matrix W. And I have the transpose there because usually our feature vectors are rows, but as a vector they're a column. So formally what we'd want to do here, kind of an objective that is very natural, again thinking in this linear projection world based on the fact that really like mean squared error, we've talked about how it's a nice error metric to use, is maybe the best thing we can do is to solve this optimization problem where we say, find me the projection matrix that goes from m dimensions down to m prime dimensions where this loses the least amount of information about our data. So in particular, we assume we're learning some projection matrix W as well as some decompression matrix that maps us back to the original space. And ideally, we would want that after we did this compression, so we've compressed X here with the W matrix, then we decompress with the U matrix, and ideally, this compression and decompression doesn't lose any information. So ideally, the difference between these two things is 0. So there's no distance between our compressed and decompressed and our original features. If this was the case, that we had 0 error here, then we could use our lower dimensional M prime dimensional features and we wouldn't be losing any information. We would just have a faster model, things would be more stable, etc. So an equivalent way of writing this in terms of matrix algebra, so X again is our data matrix, is that we're trying to minimize or solve this optimization function. So find us the compression and decompression matrices so that when we compress our data matrix and then decompress it, we don't lose any information. So in this case here, this would be the Frobenius norm because we're talking about matrices now. So luckily, this isn't that hard of an optimization problem because this is actually just solved by eigen decomposition. So in particular, to get this W matrix, we just need to find the eigenvectors of X transpose X. These are also called the singular values or singular vectors. So the singular vectors of X are the eigenvectors of X transpose X. So this is a place where actually linear algebra comes in handy, and all we need to do to perform what's called principal component analysis is get the eigen decomposition of X transpose X. In fact, if you use something like scikit-learn, under the hood it's actually going to use what's called the singular value decomposition, but the exact kind of solution procedure isn't too important. But one also important thing to know is that W is a matrix of eigenvectors. So it has all of the properties, everything you learn from linear algebra. Remember, its columns are orthogonal. There's a number of important properties. And the other thing here is that, again, we want W to compress things. So if we just got the eigen decomposition and kept all the eigenvectors, we wouldn't be compressing things at all. So we keep the top M prime eigenvectors, and the top according to their the magnitude of their eigenvalue. Yeah. Yes, indeed. So is it also an issue to decide how many eigenvectors to keep? Yes. And as I'll note in a couple slides, you generally need to do that with cross-validation. I mean, there's other ways you could also look at the magnitude of the eigenvalues. So generally, if you plot the magnitude of the eigenvalues for X transpose X, you'll see that it drops off kind of exponentially. And you don't need to worry about that long tail of really low magnitude eigenvalues. Those are usually just representing noise. What happens when you deal with, so in general, when you're doing X transpose X, that matrix is not going to have complex eigenvectors because it is symmetric and positive definite. Great question, though. Yes. So, yep. Why using the eigen? Yeah. So why do we want to select these? Yes. So we want to select M prime, 1 for making computation faster, 2 to prevent overfitting, and 3 because if we have more parameters than we have data points, that makes some learning algorithms very unstable. So if you tried to do the closed form solution for linear regression, if you had 10 million features and only 10,000 examples, you would get an error would be thrown by the solver, usually. So yeah, the motivation for this is 1, speed, 2, prevent overfitting, and 3, improve stability. Though I will say that as machine learning has progressed over the last 5 to 10 years, people used to really believe in feature selection, really believe in dimensionality reduction using, say, PCA prior to learning. But as we've moved towards these what are called end-to-end deep learning models, they kind of implicitly do this via their learning. And so generally, these days, you throw in huge feature inputs. But if you're working with, say, a logistic regression model, sometimes this can be useful. and not just improve speed, but actually improve performance. Because this is actually related to kind of the interpretation of PCA, which is that, so one view of PCA is that it's this compression matrix that causes the least amount of data loss in this linear sense. But it's also, if you're looking at the columns of this matrix, this W matrix, these are the directions. So the first eigenvector tells you the direction in your data that has the most variance. And the second is the direction in your data that has the second most variance, conditioned on it being orthogonal to the first eigenvector, and so on. And so this is useful because once you're getting down to, say, the 10,000th eigenvector, the variance is so small, and in fact, that's probably just noise in your data for a lot of data sets. So it makes sense to just throw that away, because otherwise you're just going to overfit to that noise. That's the motivation for why you want to do this. Again, sometimes it helps to keep really huge feature inputs, but there's a lot of cases where you actually want to just look at the really informative subspace. Also, if you want to visualize. So this is a toy visualization showing a data set here where, again, PC1 captures this direction where there's the most variance, and then PC2 gives the direction with the second most variance, conditioned on being orthogonal. And if you want to do a two-dimensional visualization of your data, well, getting the top two principal components is probably the right thing to do, because this is going to be the most interesting kind of two-dimensional visualization you can come up with. In fact, there are other interesting two-dimensional visualizations, but principal component analysis works very well. So just kind of a cool example of principal component analysis. This is a very classic machine learning paper. So what they did here is they took a bunch of images of faces, and then they did PCA on these faces, and now the eigenvectors of this represent what they call the eigenfaces. So here I'm showing actually what these eigenvectors, so this is the first eigenvector down to the 7th, and this is kind of the average face in their data set. So you can actually look at these eigenvectors and say, like, what are the kind of important directions of variation in this face data set. And here is another example, maybe a bit hard to see, but this is the original images, and this is what happens when we compress down to just the top 4 eigenvectors and then reconstruct back up. So if you look in the slides online, you'll see that there's actually very little compression loss happening here. And then also if you cluster in this two-dimensional space here just by the top 2 eigenfaces, you get examples that are coming from the same subject, so pictures of the same person are all clustered together. So there's a very informative subspaces, useful for feature selection, but actually also very useful and very common for visualization. So PCA, probably the most common, the most popular way of doing feature selection, of doing visualization. Yep. The difference between PCA and probabilistic PCA is outside of the scope of this course. In short, the difference has to do with probabilistic PCA. You're assuming a particular generative model over your data, and that's informing how you're doing this decomposition. But that's something where probably the math you would need would be in 652. It's an interesting, there were many variations of PCA, many kind of extensions of it, and we'll talk about some in the context of neural networks later in the course. So in addition to PCA, there are other types of feature selection techniques. There's really 2 types of approaches. One are what you can call kind of wrapper and filter approaches. So this is basically trying to actually just say, okay, I have 10,000 features, select me some subset of them that are useful, sort of filtering some out. The others, sometimes you can call them embedded approaches, and this is really regularization. So when I mentioned this L1 or lasso regularization a few lectures ago, it tends to kind of ignore some features. It sets some weights to 0 as a consequence of the regularization, and you can view that as selecting a subset of features. So you could run L1 regularized regression and say, oh, all the features that got 0 weight, let's just throw them out. So in terms of these wrapper and filter approaches, the usual thing you do is you just rank variables. You say, okay, I have a bunch of features. Which of these features are most correlated with my output? Again, through all of this, we have to choose how many features we're selecting, and the only way to do that is really with cross-validation. So one thing you might want to do is just get the correlation, so the linear Pearson correlation between all of your input features and your output target. Generally, this can work well, but if you have non-linear relationships, that can be insufficient. So a useful thing to do is to compute what's called the mutual information between your input variables and your target. So I'm showing the equation here for the continuous mutual information, and here for the mutual information in the discrete case. Very similar to all of the entropy and conditional entropy calculations that we saw before. It's basically a nonlinear measure of correlation, and formally it tells us how many bits, when I see a change in variable x, how many bits of information does that give me about variable y. And why is this good? Well, here is a little example where we have this nonlinear relationship. So we have that y is basically x squared plus some noise. Now, if we computed the Pearson correlation, so the standard correlation, the R value, as people call it sometimes, between x and y, we would get that they're almost uncorrelated. In fact, the correlation is about the same as the correlation between y and a random noise. So z here is just random noise. But if we're looking at mutual information, the mutual information between x and x squared plus noise is 1.2. So it's actually telling us that, okay, there is a relationship between x and y, between x and x squared. Of course there is, but we just couldn't see that when we were looking at linear correlation. So generally, linear correlation is not always going to be the most useful thing, but both mutual information and correlation are useful to tell us, well, I have 1 million features. I'll just quickly compute the correlation of all these features with my target and just take the top 10,000 to start with. Another important kind of drawback of all these techniques, in these variable ranking techniques, is that we're independently scoring each variable. Yep. Yep. This is a great question. So here, I mentioned mutual information and correlation, just linear correlation. But there's other metrics you could use. In practice, how do you choose which one? In the reality, you're not going to actually know that there is a quadratic relationship. Generally, I would say that mutual information is pretty good. You mentioned transfer entropy, which is also generally a pretty good one. Unfortunately, this is one of those cases where it's all domain intuition. And in fact, I'm personally an advocate of regularization rather than these sorts of wrapper and filter selection approaches. Again, these can be useful for kind of discarding really useless variables if there's zero mutual information. But generally, I would say go for something like mutual information unless that's too expensive. Transfer entropy is a very interesting thing that can be very cool, but I think isn't going to give you much gain over just using mutual information. So I would say generally mutual information if you can afford it over Pearson correlation, but other than that, I think that usually I would advocate using regularization over these techniques, frankly. I mention them because they're important kind of background things to know. So one other issue and one reason why I think these techniques have limitations compared to, say, regularization is that we're getting all these correlations independently. So we're trying to say how correlated is feature 1 with the target, feature 2 with the target. That doesn't take into account any interactions there is between these variables. And really what we want a subset of the features, not just a bunch of independent features. And these subsets might work better or worse together. So what you really want to do is the best subset selection. And here things get very difficult because there's 2 to the m possible subsets of these features. There could be interesting interactions between all these features, especially if you're using nonlinear models. So in principle, you have to consider all possible subsets. And this search space is very large, so here is a visualization of, say we start with no features, we could add this feature, we could add this feature, so on and so forth. And in practice, if people actually do run these sorts of correlation or mutual information-based techniques and do some subset selection trying to figure out the best subset of features, you have to use some sort of smart technique, like a search algorithm you might see in, say, Comp424, or a genetic search algorithm, or use domain knowledge to group your features together. And again, I will say that personally I'm a bit more of an advocate, and the wisdom of machine learning in the last few years is that regularization, so adding L1 or L2 or both to your model, if you can afford to run the model with that full set of features, just regularizing them, that is just a better thing to do than trying to throw features away before running your model. So regularization, again, is controlling your complexity, helps you not overfit without the cost of throwing away features. It's still going to cost you computational complexity, but it's going to help you not overfit, and if you can pay the computational complexity, it's almost always better to regularize rather than to do feature subset selection. And just to remind everybody, we're doing all of this feature subset selection, etc., on the validation set. At the end of the day, you run things on the test set, but we're figuring out what our right feature subset, what features to construct, so on and so forth, using just the training and validation data. And if people are interested in kind of a bit more discussion of this, and especially kind of a classic discussion of this, I have a link to this paper here. It's a very classic machine learning paper discussing variable and feature selection. And as I mentioned a few times throughout this lecture, some of these things, in particular the subset selection work, is not really in vogue anymore as much. PCA people still use all the time, but again, more and more these days we're moving towards models where we throw in the whole kitchen sink of all the features into an extremely complicated nonlinear model, some sort of deep neural network that we regularize in smart ways, and we just hope that that thing implicitly does good feature selection for us. So these are good things to know, but also good motivation for what will be, again, kind of the second major unit of this course on deep learning. That's all for today. Thanks.